So, well, thank you for inviting me to be part of this WISE meeting. I'd like to say that I think I learned a lot. The last one I was at was at least 20 years ago, so that's a long time. No, in Brest. I think we had one, yeah. So I can see lots of things have changed, and I would like to see whether we can make the connection with the nearshore also a little stronger. So so I have actually have an introduction into nearshore waves. Like with many other titles, Fabrice is the one that came up with the title. It is I would say, a little bit pretentious, this title. So I'm not going to talk about everything in nearshore waves, and I actually try to make something that you can see as an introduction into nearshore waves, and then specifically what happens into the surf zone. As you can see, I have many collaborators that I put here on the right, so this is really a combination of work that a lot of people have done. Feel free to ask questions while I'm during the presentation. If there's lots of questions, then I won't get to the end of the presentation, but so be it. Okay? So, to give you an idea, I actually use XBeach as one of my media to explain the dynamics of nearshore waves. And I will consider three different modes. One is what we call the wave average, so basically stationary mode. A wave group resolving mode, so where you can see the wave groups, and you can also run this model in what we call intra-wave or wave resolving. And XBeach is not the only model. There's many models that can do similar things, but this is just to give you an idea. And then I would like to look at wave transformation, the wave setup, and in that respect also wave run-up, but that's what I'll get to at the very end. I like wave groups and infragravity waves, so I've tried to squeeze some of that in here. And so at the coast, most coasts are not necessarily sandy beaches. We have all sorts of coasts. I was in Brest a couple of weeks ago, and then hey, depending on where you are, it's sandy, it's rocky, there's cliffs, there's vegetation, etc. And ultimately, people want to know, okay, am I safe or not? How high is the water going to be, and will these waves be surfable or not, or should I be away if it gets too big? So really, we need to understand how the waves interact with the different features at the coast. So I'll talk a bit about interaction with vegetation, because we happen to work on mangrove coast, for example, and also coral canopy, if time permits. So these different modeling modes, so if this should be timed, so this is the three different modes that you can do in SurfBeat. The dark color is, let's say, the instantaneous wave height. So in the top panel, you can see that that is constant, because we do wave averaged. I think there's also a pointer there too, right? Yeah. The solid line, the solid black line, is the mean water level, and you'll see that the mean water level is actually going up towards the coast, because this is where the waves are breaking and they push the mean water level up. This is what we call the wave setup. Probably everybody knows this. Then we have a version that actually allows you to look at the wave groups. So now the wave energy is not constant, but it's actually varying in time. And as a result, there's also a variation in the wave height in time. So again, the black is the wave height. And then, sorry, the dark blue is the wave height. And then the black is the water level that's associated with these wave groups. So you'll see that if the waves are high, then we sort of expect a depression. It moves towards the coast, the waves are breaking, and then actually it gets quite complicated, because that's where these long waves are being released, reflected, etc., trapped. We'll call that the wave group resolving mode, and then the final one at the bottom is where we resolve all the waves. And in this particular case, you can see that you start with something that is deeper waters, more or less sinusoidal. You get steeper waves, so basically Stokes type waves, and then as you get to the coast, they become asymmetric and they break. In principle, this mode has everything in it, but it's all, and actually most of my talk will be all 1D. So we're just looking at a beach that is actually quite simple. So to start with something really basic, I'm going to look at the wave average energy model. So this is the mode where we assume everything is averaged. And we had a lot of presentations about energy flux. So here there's an overbar. So what's really different is that in the wave action equation, we look at the energy as function of frequency direction. This particular case, everything is just integrated, and we pick a representative direction and a representative frequency. So typically like the peak frequency. The dissipation, we had many talks about dissipation, all related to white capping. I'll talk about dissipation due to depth limited braking, because the bathymetry is really one of the controlling, let's say, facets in the nearshore if we talk about wave propagation and dissipation. For this particular case, we have the energy which you can express as the root mean square wave height. To say something about the dissipation, the analogy with a bore is made. So this was done by Bartjes and Janssen. And basically, if you look at a braking wave, so this purple blob may not be the best color, but that is, let's say, the bore. The height of the bore is assumed to be similar to the height of the braking wave. And then you can calculate what the corresponding dissipation is. Now, waves are irregular, so even though we are working with a stationary model and we have a root mean square wave height, we need to know how many waves are breaking. So if you know the root mean square wave height and you define some sort of maximum wave height, that is, let's say that is the depth limitation, then you can calculate the fraction of breaking waves. So this is one of the earliest models by Bartjes and Janssen. So if you take that into account, you can calculate the total dissipation, which is now depending on the fraction of breaking waves and a representative wave period. And then there's two parameters in there. There's an alpha and a gamma. And alpha is typically taken 1, and this gamma thing, that's all over the place. So that there's been a lot of effort in trying to figure that out. I want to show you something about what we've done in the past. So again, to show you the importance of bathymetry, and I'll get back to that later too. So these are experiments at Duck, Sandy Duck. The objective was actually to look at bar dynamics. Nature is not doing, was not doing the things that we wanted it to, because if you look at the bottom profile here, there's actually no bar. That made it from a bar morphodynamic perspective not the best experiment. But the nice thing is that it's more or less a Longshore uniform. So you can see the depth contours here. And for this particular case, we have an array of pressure sensors. This goes about to -4 meters depth, but there's also then the FRF array, which is 8 meters depth, which gives you the boundary condition. And then we could use these pressure sensors to estimate the corresponding root mean square wave height. So those are the circles. And then we can use the model that I just presented to compare with the observations. So for this particular case, I actually optimized this gamma because I was interested in the return flow. I'm not talking about the return flow today, but the objective was to basically get a very good estimate of the return flow, which is a function of wave breaking and the mass flux. So if you optimize it for this one beach and these conditions, you get a gamma that varies between 0.6 and or the mean is 0.6 and a variation of 0.15. And for the, which may also be important, so for the model, I just can get the root mean square wave height from the mean energy. But from the measurements, I have to translate the pressure. So I have the pressure spectrum. I use linear wave theory to translate that to surface elevation. And then I actually integrate over a certain frequency band. so from 0.05 hertz to 0.3 hertz. And that means that the lowest part is actually excluded, which contains the infragravity waves. And it seems trivial, but it makes a lot of difference whether you include it or exclude it, especially if you're in the surf zone. So given just a discussion about significant wave heights, if you do it in the surf zone, it makes a lot of difference what your integral domain is. Whether you include the infragravity waves. So this is excluding infragravity waves, and then, well, if you optimize it, of course, you get a very good correspondence. If you use a parameterization, so this is the one by Batjes and Stiever, then you'll probably get more of an error, but my experience is that it actually is working pretty well. So then, in that case, you need to relate it to the deep water wave height and the deep water wavelength. So there are many of these parameterizations, and I'll mention a few in a minute. Then I would like to say something about the setup. So we've averaged over the short waves. So the overbar is again average over the short waves. These velocities are actually, let's say, the infragravity velocities and the mean velocity. So the capital U is let's say, the slow modulation of the velocity. This is the radiation stress, which is given to us by Longray, Diggins, and Stewart, which is something that we can calculate based on the orbital velocities and the pressure. And it's been shown that you can express that as a function of the energy and the group velocity and the phase velocity. So if we simplify this, so let's say we look at stationary conditions. So we take out the time derivative. We actually ignore the nonlinear term in the velocity. We also ignore mixing, and we ignore the bottom shear stress. Then we get up a balance between the pressure gradient and the radiation stress gradient. Typically, ignoring these terms is not a problem. The bottom shear stress, we know, actually affects the setup, but it also depends on the friction. And what you see here basically is if the radiation stress goes up, you know it's a function of the wave height and the energy, then you expect that the mean water level is going down. So this is what we call the set down. And then when the waves are breaking, so this is an experiment by Bowen, you see the waves breaking, the radiation stress decreases, then the water level goes up. So this is the setup. So at the mean, let's say the time averaged time scale, we get a balance between the set up, set down, and the radiation stress. Okay, so we have a bulk model, and that tells us something about how this, how much of the energy is dissipated. It's still partly empirical, but let's say now we have the dissipation. We would like to distribute that over the spectrum because ultimately what's coming in can be represented by a frequency directional spectrum. And there's different ways of doing it. What we tend to use at the moment, for instance, in SWAN, is making it linear proportional to the variance. So we have, this is from Leo Holthuizen, his book, which I borrowed. So let's say the John Schwab spectrum is the dashed line. That gives you an idea of the variance at that location. And the corresponding dissipation is linearly distributed over the spectrum. So you can also make it frequency dependent, and there's arguments why that should be the case. You can partition it in frequency. You can also partition it in direction. So there's many options that you can take, and depending on the conditions, they can lead to an improvement or not. Okay, so this distribution, of course, because we talked about triads, a little bit, mostly about quadruplets, but also triads. Depending on the triad interactions, how you formulate your dissipation in frequency and directional space is going to affect your spectral evolution. I mentioned alternative models, so there's, I think most people know Thornton and Guza if you're from the Nearshore. There's also Tom Baldock made his model. There's Janssen, Batjes, Alsina, and Baldock. So there's many more that are based on similar concepts. So based on, let's say, the distribution of the waves and the distribution of the breaking wave heights. Then this gamma parameter. We have a whole range of people that looked into optimizing the gamma depending on let's say, the conditions that are at play. What is important from a morphodynamic point of view, because my background is also basically in how the beach changes, is there's two elements. So one is the breaker delay, that is the fact that in the surf zone it takes a bit before the wave actually breaks, which is what we call breaker delay. And the other part is this bore that I talked about. So let's say the energy and the momentum from the breaking wave gets transferred into a bore, which is then subsequently propagated at the phase speed of the breaking wave. And these bores, they are important for driving return flow, also longshore currents, but also anything that is floating in the surf zone, which is my lead-in for EJ's talk, which is coming up. So looking at plastic transport, for example. So that is not part of the typical breaking, but that is definitely something that's important. And then the thing I struggle with a lot nowadays is infragravity waves. So I told you that we're looking at infragravity waves with time scales of, let's say, 25 seconds to 250 seconds. And they not necessarily disappear in the surf zone. So it really depends on the dynamics or on the particular, let's say, configuration of your bed profile and the dynamics of the infragravity waves, how much of that is being dissipated, how much of that is actually being transferred back to the sea swell frequency and then dissipate, or how much of that is being reflected. And that's not something that you can just put in a dissipation model. And all of this is really controlled by the local bathymetry. So, I mean, if you don't know the local bathymetry, you're basically lost. So there's a lot of interest in retrieving or trying to get a handle on this local bathymetry. And I'd like to mention a few more recent developments. So there's the work by Luijendijk et al. And by Kilian Vos is using satellite observations to look at shoreline evolution on a global scale. So that actually will give you some information about, let's say, the general shoreline, but also about things like the slope, which is important for reflection properties, for example. But what we need from, let's say, if you really want to model in the surf zone, is actually the full underlying bathymetry. And so far, we've used mostly jet skis, where you take a jet ski, echo sound, a GPS, and you move around and you try to measure the bathymetry. That is very tedious, and so there's, I would say, some promising alternatives that are being developed where they're trying to actually estimate the bathymetry from either optical instruments, like what's done here, I think, with Raphael Lamar, but also drones and there's other mechanisms. But ultimately, what we need is really so the green part is the bathymetry. This is inferred and this is measured, especially the bar profiles and things like that. That's the part that we need. Not to mention that there's also muddy coasts, mangrove coasts, etc. All right, then I'd like to move to this next mode. So now the wave energy is allowed to vary on the timescale of the groups. So basically we have an extra term in there that is the time variation. The energy is, you could say, is a combination of the mean energy, which is what we already had, and a modulation at the wave group energy. And this is slow because we're looking at wave groups. So this is an example of the wave group. This is something that I made up. It's not a regular wave group. I say this is actually a very regular wave group. This is not a real wave group. And what you see is that the surface elevation is changing in space. You take the envelope, and that will give you your wave group, and envelope squared you can relate to the energy, and hence your energy balance. Where the energy is high, the radiation stress is also high. We tend to get a depression, and it's a bit difficult to see, but this bound wave, which I'll get to in a minute, is traveling with these wave groups as it goes into the surf zone. And in the surf zone, this modulation is disappearing because of wave breaking. And there's discussion over how this modulation disappears. But you can imagine that if there's no forcing, then this wave, this bound wave that was attached to the groups, is free, and it can be reflected. Again, the time scales that I'm talking about is between 25 seconds and about 250 seconds. So similar to the wave momentum for the mean, I now go to the wave momentum at the wave group scale. So again, now I have a time variation. So this is the infogravity velocity. I look at the continuity equation, I take the linear version of the momentum equation, and I combine it, and I get to the long wave equation. So on the left, let's say we have the expression for the surface elevation. So by combining these, it's all expressed as function of eta, which is now the, let's say, the combined mean, the sort of setup and the wave motion. And on the right-hand side, I have the forcing by the radiation stress. And this is relatively simple because everything is 1D. In reality, of course, this is not the case. We have obliquely incident waves, and it gets a bit more complicated. This is an example. So let's say we're offshore. This is our wave group, and let's see whether this works. Oh, sorry. The radiation stress. So we saw that the radiation stress can be related to the wave energy. And what I'm doing is this wave energy is a combination of the mean and the wave group energy. And this delta omega and the delta k are the difference frequency and the difference wave number. So for this particular case, I have two components with two different wave periods, so that'll determine the delta omega. And because of the dispersion relation, they also have a different wave number, and that is the delta k. So the way you can see it is delta omega determines the, let's say, the length of the wave group, the duration of the wave group, and delta k determines the length of the wave group. So with this forcing here on the right-hand side, I can actually submit a solution that will give me what I call the bound long wave. So what you see here is on the left is the bound long wave, where eta hat b is the amplitude. And it's 180 degrees out of phase with basically the radiation stress and the wave energy. So where the wave energy is high, the bound long wave has its minimum. So that's what you see here. So energy is high, the bound long wave has its minimum, and where energy is low, it's the opposite. And you can see from this solution that it's actually, so the propagation is determined by this delta omega and delta k, and that also is the same, so it's in phase with the propagation of the groups. So what we expect to see is that this pattern of waves, of wave groups, is accompanied by this bound long wave that is propagating with these wave groups. And yeah, of course, because I made this simulation that's working, but this is sort of what you expect to see. Okay. I mentioned something about the release of these bound long waves. So if we just look at the expression for the bound long waves, then the amplitude should vary with the forcing, but it also depends on the difference between the let's say the free long wave speed, so the square root of GD, and the group velocity. And in fact, from this expression, you can see immediately that if the group velocity goes to the free long wave speed, you have an infinite solution, so it blows up. If we're in relatively shallow water, we can approximate this group velocity as a function of the depth and kd. And if you substitute that, then you'll find that the amplitude of the bound-long wave should be dependent on the water depth to the power of minus 2.5. So it's actually very sensitive to the water depth. So you expect it to grow fast if the depth decreases. Yeah? These are the results of experiments that were done by Van Oorloos and analyzed by Batjes and Van Dongeren et al. And what you see, so they made a parameter, beta b, which is a function of d sub x, which is the slope, so that's the bed slope. This delta omega that I talked about, and the depth at which the waves are breaking. And what they show is that if this was right, if this is true, then all of these results should be lying on this particular line here above. So that's if the bound-long wave would evolve according to this expression. Turns out that that's not the case, and it really depends on the particulars of these parameters, how it evolves. And what you see here is that, let's say, if the slope is really small, so let's keep delta omega the same, and the slope gets really small, then you have a very mild beach, and in that case, the bound-long wave can keep up with the forcing. So then you expect to be in this regime. Whereas if the slope is quite steep, then you're in this regime, and basically this bound-long wave has no time, space to adapt to the forcing, and it doesn't grow. And then for the free long wave, we can just look at a simple energy balance where we take the group velocity as the free wave speed, and then we expect that that should be corresponding to a much weaker dependence on depth, and that is confirmed by this. So, what does that mean? It means that the bound-long wave is expected to grow faster than the free-long wave as it decays, and I'll get back to that. Then the other thing I talked about was this dissipation of the infragravity waves as you get into the surf zone. Typically, if you talk about wave reflection, then you would consider the wave that's coming in, and let's say the energy that's coming out, and then you can use that to estimate your reflection. Because of this behavior of the bound long wave and the free long wave, that reflection is actually much more complicated to express. And what we see is that this reflection also, again, depends on this ratio of the slope and this delta omega. And for that, they introduced a slightly modified parameter. But again, it depends on this ratio. So this basically the relative slope of your bound wave height or your incoming infragravity wave height, and the bottom slope that controls the reflection and also the growth. So we see that for beta values of less than 1.25, we have partial reflection. So full reflection is at 1. And in this particular case, you see that it ranges from 0.1 to 0.7. In these cases, where you think that actually the reflection is less because of bottom friction. So, going back at duck, so what does it mean? Let's say the blue one is my incoming bound wave, or wave group force infragravity wave. That is growing with the decrease in depth. If it would be fully reflective, then in that case you would expect actually that a free outgoing wave is dominant because that is much less dependent to depth. But if you look at the numbers, then you'll see that the reflection should be about 0.8. So as a result, there's a reduction in the reflected wave height, but still you'll see that if you go somewhat offshore, that it's dominated by free outgoing infragravity waves. It's just what they found. But it really depends on the particulars of your beach. So just happens to be the case in this scenario. But if you go to a different beach, you could use these parameters to say something about what you expect. And there are beaches where it's mostly dissipative, also for infragravity waves. Okay, why do I really want to know this? And that has to do with ultimately the run-up and overtopping and associated overwash and dune erosion. So in the Netherlands, we have a system in place where we do a 5-year assessment of the safety of the Dutch coast, including all the sandy dunes. And for that, X-Beach is being used. So we are really trying to develop these models so that we can make predictions about what is happening to these dunes under extreme conditions. And this is an example based on the work of Robert McCall, where I have now it's a 2D model of X-Beach, and this is actually the surface elevation of the infragravity waves. So the top part is the surface elevation of the infragravity waves. This is the bathymetry and the topography. This is Santa Rosa Island, by the way. What you see here at the bottom are the tidal elevation and the wave conditions. It's a bit difficult to see because it's in dark green and dark blue. What we won't talk about today is all of this is coupled to sediment transport and morphodynamics. So it tells you basically how the beach is changing. All right, let's see what it is. And this is around the time of overwash. So this is the peak of the hurricane. You have high water levels. And the thing is, what you see is that these infragravity waves, as they propagate towards the shore, they get bigger. But it's really the infragravity waves that determine the elevation at the waterline. And then when it is high enough, then you can initiate this overwash regime, and in this particular case, it also gets to inundation. So now, the water just passes over. And you have full overwash and inundation. Infragravity waves are also important for ship motions, harbor resonance, sea ice, as we've seen, and also vegetation. Which brings me to the next part. So I told you, so we're doing an experiment in Indonesia, actually, where we're looking at, we're trying to help in restoring the mangrove forest. And the reason for doing so is because if you have vegetation, it actually can help protect the coast. So we would like to understand how that can help us and how we can make it so that we can be safer. This is work done by Arnold van Rooyen. And I'm going to do this again at the wave group scale. So you can do this at let's say the wave average scale, but you can also do it at the wave group scale, and you can do it intra-wave scale. So remember again, so this is at the time scale of the wave groups and therefore infragravity waves. So this is also modulated at the time scale of the infragravity waves. And we have an interaction with vegetation. So what you see over here is basically the drag that is exerted on the vegetation. And it depends on the height of the vegetation, the diameter of the vegetation, and the particulars of the waves that you're looking at. And then this drag coefficient, this C sub D, which is again something that is quite empirical. So there's a lot of research into finding, let's say, optimal drag coefficients. And this N sub V is an indication for the number of, basically the density of your vegetation. And so what I'm going to do is we're going to take the velocity and split it into let's say, the infragravity and mean velocity and the orbital velocity, and substitute it into this drag force. So then you get two components, one related to the waves, and one related to the mean and the infragravity velocities. And now the wave skewness and asymmetry comes in. So if you have linear waves, then so the overbar is the time averaged, then you expect that net contribution is 0. But if you have nonlinear waves, like Stokes waves, then that is not zero. So the shape of the waves has affects the forces that are being exerted on time averaged on the vegetation and vice versa on the water. So let's say if we take Stokes waves, we actually know that the peak velocities are higher than the crest velocities. So the nonlinear contribution is expected to be greater than zero. So the funny thing is that if you have Stokes waves, you actually expect, because then this term becomes positive, because there's a minus sign, you expect that the setup is actually going to be reduced. So the nonlinearity of the waves affects the mean setup of the water level. Because this is a wave group model, we don't have the phase. I mean, so there's no information about the nonlinearity. I mean, you would get it if you would do an intra-wave model. But we can just make a local approximation based on what we use here is actually Reniers and Fenton. So we take, you know, basically we take the wave height in a given period, we reconstruct the velocity, and then we need to have the phase, and this phase is going to determine whether it's a Stokes-like wave or whether it's more like a sawtooth wave. And for that we use a parameterization. So because we don't resolve it, we have to parameterize it. And for that we use the work of Gerber, Russink et al. We also have dissipation, so that was the momentum. Because of the interaction, the work done by the force on the vegetation, we also have a loss of energy. So at the wave group scale, we get a dissipation due to braking and one associated with the vegetation. And for that, we can use the work of Dalrymple et al. And Mendes and Losada. And then we can start comparing. So this is a comparison between model output and observations. The black lines are without vegetation. The solid yellow lines are vegetation and this nonlinear wave shape. And the dashed yellow lines are vegetation and no wave shape model. And you can see that for, so whether or not you include the, let's say, okay, let me start with the vegetation. So the difference between the solid line and the yellow line is the difference with and without vegetation, just for the wave energy dissipation and therefore the wave height. So would say that that compares well. The next one is the infragravity waves. And what you see is that without vegetation you get the black line. And if you include the vegetation, we see a reduction in the infragravity response. So, vegetation location, which I didn't, so it's actually corresponding to these dots at the bottom. So that's where the vegetation is. The biggest difference we see at the setup, and this is so the model without having this nonlinear correction would tell you that the setup is according to the dashed line, whereas the measurements tell you that that is actually not the case. So if you have vegetation for this particular case, the measurements show that the setup is much more limited in the presence of vegetation, and if you include the wave shape, you do get the right results. So this is just to summarize, because this is, let's say this is one single computation, but with this model, of course, we can look at different heights of the vegetation, where it starts. So this is actually the water depth at the start of the vegetation. So basically, if you started earlier, and this is the slope. And really, what I want you to look at is, so this is, let's say, the model where we include the wave shape, and this is the model without the wave shape. And you can see that that this setup is significantly reduced to the case where you do not include the wave shape. So it allows you to run it on a wave group scale, but still get good estimates for the setup. Yeah. Okay. You haven't asked any questions, and still I'm quite close to the end. All right. So quickly something about the wave resolving part. So now we use it in non-hydrostatic mode, and we're going to look at what happens on a reef. So we have waves coming from offshore. There's breaking on the reef. There's release of infragravity waves. They go towards the beach. Some of that was reflected. Some of that is dissipated. And the interest is really on what happens if the coral reef is degraded or not. So this is a work of Stuart Pearson and co-authors. And what we show here, just to get to the results quickly, is that apparently that's not working. Oh. I think we're done. It's anyway. Yeah, no, I can't go forward.